You wanted a deep dive into the world of quantum computing. And you know what? The reality is even more mind-boggling than any sci-fi movie out there. Today, we're going to explore how these machines, which could revolutionize everything from medicine to material science, could actually get built. We'll be using excerpts from a research paper titled Artificial Intelligence for Quantum Computing by Alexeyev et al. To help us make sense of it all.
And what's really fascinating is how this research showcases the merging of two incredibly complex and powerful fields: artificial intelligence, or AI, and quantum computing.
It really is like witnessing the ultimate scientific superhero team up. But before we get too far ahead of ourselves, can we back up a bit? You mentioned the potential of quantum computers, but building these things can't be easy.
You're absolutely right. To give you an idea of the challenges involved, imagine trying to run a program in a room full of screaming toddlers. That's basically the level of noise that quantum bits, or qubits, have to deal with.
Okay, that's a pretty chaotic picture. So mitigating that hardware noise must be a major hurdle.
It is, and designing those qubits to work together efficiently, that's a whole other layer of complexity.
So where does AI come in? Is it really up to the task of tackling these monumental challenges?
Well, it's already showing incredible promise. One area where AI is already making a big difference is in creating more robust control signals. It's basically teaching those qubits how to function, how to speak, so to speak, even with all that noise around.
That's remarkable. So AI is like a quantum noise-canceling headphone, helping those qubits find their voice amidst all the chaos.
That's a great way to think about it. But AI's role goes way beyond noise reduction. Think about the incredibly complex task of tuning and characterizing these quantum devices, something that usually requires tons of time and specialized expertise. AI is stepping in to automate that process, and it's already significantly speeding things up.
It's like having an AI mechanic, making sure these incredibly sensitive devices are running smoothly. Are there any other examples of how AI is being used to overcome these hardware challenges?
Absolutely. Researchers are using AI to design entirely new setups for generating what are called entangled states.
Now, I know entanglement is a pretty wild concept, but I think our listeners have at least a basic idea of what it is for our purposes today. Maybe you can just explain why these entangled states are so important.
Entanglement is key because it allows qubits to influence each other instantaneously, even if they're physically far apart. It's like they have an invisible connection. And AI is helping us not only create these entangled states, but also control them, a crucial step towards unlocking the power of quantum computation.
So we've established that AI can help us design and build these incredibly complex quantum computers. But what about the algorithms they'll run?
That's another area where AI is proving to be indispensable. Quantum algorithms, which are basically the sets of instructions for these computers, need to be incredibly efficient to work on the limited hardware we have today. One of the big challenges is reducing the number of quantum gates needed, because each gate introduces the possibility of error.
So it's a bit like finding the most elegant path through a quantum maze. The fewer steps, the better.
Exactly. And you know what? AI is turning out to be a master maze navigator. Take Google DeepMind's Alpha Tensor Quantum, for example. It used AI to find a more efficient way to do matrix multiplication, which is a really common operation in many quantum algorithms. They essentially found a shortcut in the quantum code.
That's amazing. But even with the most elegant algorithms, we're still going to run into those pesky errors.
You're right. Error correction is absolutely vital if we want to build reliable quantum computers. It's like having a spell checker for quantum calculations. But here's the problem. As quantum systems scale up, our traditional error correction methods really struggle to keep up.
So as these systems grow larger and more complex, we're going to need a much more powerful spell checker.
Exactly. The research paper actually points out that traditional decoders, which are the algorithms we use to identify and fix errors, would need to work faster than even the fastest supercomputers we have today to keep up with all the potential errors in large-scale quantum computers.
That's a pretty daunting thought. It sounds like we need some kind of quantum miracle to happen.
Well, as luck would have it, AI might just be that miracle. AI is being used to develop an entirely new generation of decoding algorithms, ones that are faster, more accurate, and can handle different kinds of errors.
So it's like AI is giving us a supercharged error correction system, one that can handle the massive complexity of these quantum computers.
Precisely.
This is also fascinating. It seems AI is involved in every single stage of building and using these quantum computers. But to get a clearer picture of how this all works, I think we need to look at some of the specific AI techniques being used. What do you say we dive into some of those details?
I'm ready when you are. Welcome back. Before the break, we were discussing how crucial AI is in the realm of quantum algorithms. Let's dig into some of the specific techniques at play, starting with quantum circuit synthesis.
I have to admit, that sounds a bit intimidating. What exactly does quantum circuit synthesis involve?
Think of it like trying to write a recipe, but for a quantum computer. Instead of ingredients, we're using quantum gates, which are like the basic building blocks of quantum circuits. The goal is to find the best possible sequence of these gates to carry out a specific calculation.
And I'm guessing figuring out that sequence isn't exactly a walk in the park.
You got that right. The number of possible combinations explodes exponentially as the number of qubits increases. It quickly becomes a ridiculously complex puzzle, and that's where AI steps in. Deep learning techniques are being used to automate this process, allowing researchers to explore a much wider range of possibilities and discover solutions that are far more efficient.
So it's like having an AI chef who can whip up the perfect quantum meal, finding that ideal combination of ingredients, or quantum gates in this case, to create something truly remarkable.
That's a great analogy. And one of the most exciting advancements in this area is the use of generative AI models. Imagine training a model on a huge library of existing quantum circuits, and then having it generate completely new circuits that meet specific requirements, like using the fewest gates possible, or maximizing the accuracy of the calculation.
Okay, now that's seriously impressive. Do you have any real-world examples of these AI-powered circuit synthesizers in action?
Absolutely. There's a model called GPT-QE, which stands for Generative Pre-trained Transformer Quantum Eigensolver. Essentially, it's a large language model that's been trained to understand the language of quantum circuits.
So it's like ChatGPT, but for quantum computers?
Exactly. You can give GPT-QE a description of a problem, like figuring out the lowest energy state of a molecule, and it can actually generate a quantum circuit to solve that problem. What's even more remarkable is that these AI-generated circuits are sometimes even more efficient than those designed by human experts.
It sounds like these AI models are going to completely change how we create quantum algorithms. But even with these incredible advances, we still have the practical challenges of running these algorithms on real quantum computers.
Right.
And that brings us back to error correction.
You're right. Error correction is going to be a constant companion on this quantum computing journey. We touched on this earlier. But as quantum computers become more complex, traditional error correction methods simply can't keep up.
So what's the solution?
AI, of course. It's being used to create a whole new breed of decoders, which are those error-fixing algorithms we talked about. These AI-powered decoders are not only faster and more accurate, but they can also adapt to different types of errors, something that's essential for building robust quantum computers.
It's like our quantum spell checker is getting a serious upgrade, thanks to AI. But how are these new decoders actually learning to fix error?
They're trained on data from actual quantum devices. This allows them to learn how to predict and correct errors in real time. And even better, they can adapt to new types of noise as they encounter them. It's a huge step toward making quantum computers more reliable.
That's pretty amazing. So AI is helping us not only build these quantum computers and design the algorithms, but it's also helping us ensure those algorithms run smoothly. But what happens after the calculation is done? How do we make sense of the output?
That's a critical point. The output from a quantum computer isn't exactly easy to decipher. It's like getting a message in a language you don't understand. And that's where AI comes in again, this time in the form of quantum state tomography.
Okay, break that down for me. What is quantum state tomography and how is AI involved?
Essentially, it's the process of figuring out the quantum state of a system based on a bunch of measurements. It's a really computationally heavy task, but AI is helping us develop techniques that are more efficient and accurate.
So we're using AI to decode the secrets hidden within the quantum data. It's like having an AI archaeologist on hand to help us understand these cryptic messages.
I like that analogy. And one of the really cool ways AI is being applied here is through the use of convolutional neural networks, or CNNs. These networks are particularly good at finding patterns in images, but they've been adapted to work with quantum data too. What's remarkable is that they can reconstruct quantum states with incredible accuracy, even when the data is limited.
It's mind-blowing how AI seems to have a solution for every challenge we encounter in this quantum realm. It truly is the ultimate quantum sidekick.
But are there any other areas in quantum computing where you see AI playing a role in the future? Areas that maybe we haven't even thought of yet?
That's the really exciting part. The potential applications of AI in quantum computing are vast and still largely unexplored, We've only just begun to scratch the surface.
I'm definitely getting the sense that we're just at the beginning of this incredible quantum AI journey. What are some of the areas you're most excited about in terms of future research? One area that really captures my imagination is the development of AI-powered quantum supercomputing systems. Imagine quantum processors working hand in hand with AI supercomputers to tackle problems that are simply impossible to solve today.
That sounds like something straight out of a science fiction movie. But I imagine there are some pretty big hurdles to overcome before that becomes a reality.
Oh, absolutely. Building these hybrid systems is going to require major advancements in both the hardware and software. We need to figure out how to seamlessly integrate quantum processors into our existing supercomputing infrastructure, and we need to develop new programming models that can take advantage of both quantum and classical computing.
It sounds like a monumental task. It's also an incredibly exciting challenge. Are there any other obstacles you foresee on this path?
One of the key challenges is going to be getting enough high-quality data to train our AI models. Most of the AI techniques we've discussed rely heavily on having vast amounts of quantum information to learn from. But getting that data from real quantum devices is still incredibly expensive and time-consuming.
So we need to find a way to generate more data without having to run endless experiments on these expensive quantum computers.
You got it. And one promising avenue is using quantum simulations. We can use classical computers to create virtual quantum systems, generating synthetic data to train our AI models.
It's like creating a virtual playground for our AI models, where they can learn and experiment without the limitations of real-world quantum hardware.
Exactly. And here's the cool part. AI can actually help us create even better simulations. Researchers are developing AI-powered quantum simulators that are far faster and more efficient than traditional methods.
So AI is not only helping to advance quantum computing, but it's actually helping to advance itself in the process. It's a truly remarkable cycle of innovation. But beyond these technical challenges, are there any other potential roadblocks to this quantum AI future that you're concerned about?
I think one of the biggest factors is going to be the need for much stronger collaboration between the AI and quantum computing communities. Right now, these fields are relatively separate, each with its own specialized knowledge and expertise.
So it's like we have two separate superhero teams that need to learn how to work together to save the world. We need to assemble the ultimate quantum AI league.
Exactly. We need to foster more research that brings these fields together and encourage the sharing of ideas and insights.
This has been an incredible deep dive so far. It's amazing to see just how much potential there is at the intersection of AI and quantum computing. You've given us a lot to think about, and I'm sure our listeners are eager to hear more about what this all means for the future. After a quick break, we'll wrap up our exploration of this exciting frontier and leave you with some thought-provoking questions to ponder. Don't go anywhere. Welcome back. We've spent this deep dive exploring the amazing synergy between AI and quantum computing, and it's clear these two fields have the potential to completely change science and technology as we know it.
What I find particularly exciting is that we're still in the very early stages of this quantum AI revolution. There's so much more to discover, so many possibilities that are still out there.
It really feels like we've only just started to explore this vast, uncharted territory. To wrap things up, let's talk about what the future holds for this dynamic duo. The paper we've been discussing highlights some really intriguing ways AI could be used in quantum computing, especially when it comes to error correction.
Right, as we've talked about. Error correction is absolutely essential if we want to build quantum computers that are reliable. And AI is already showing us new ways to develop much more sophisticated decoding algorithms. But the research suggests AI could go even further. It could help us design completely new types of quantum error correction codes.
So instead of just fixing the errors, AI could actually help us design quantum computers that are much less prone to errors in the first place. That's a fascinating idea.
Exactly, up until now. The design of these error correction codes has been a slow, manual process that relies heavily on human intuition and expertise. But AI has the potential to automate this, allowing us to explore a much larger range of possibilities and maybe even discover codes that are far more efficient and robust than anything we could have imagined on our own.
It's like AI is becoming the architect of the quantum computer, designing the blueprints for a machine that's inherently more stable and reliable. I'm curious, does this idea of AI designing quantum systems extend beyond error correction?
Absolutely. Researchers are also looking at how to use AI to design entirely new quantum algorithms.
Hold on, you're saying we could have AI actually creating the recipes for quantum computers, not just tweaking the ones we already have. Could you walk me through how that would even work?
It's a really complex challenge, but AI is surprisingly well suited for this kind of task. AI algorithms are incredible at finding patterns and making connections in huge data sets. We can use this ability to train AI models to understand the fundamental principles of quantum mechanics and quantum computation.
So it's like we're teaching AI to think like a quantum
That's
physicist.
a great way to put it. And
Yeah.
once we've done that, we can essentially unleash these AI models to explore all the different possibilities, searching for new quantum algorithms that give us a real computational advantage for specific problems.
That's incredible. It seems like AI could be the key that unlocks a whole new era of scientific discovery and technological innovation. But I have to ask, if an AI is designing these quantum algorithms, who gets the credit for the discovery? Is it the AI or the people who created it?
That's a big question, and one we're going to have to think about carefully as AI becomes more sophisticated and plays a larger role in research. It's a question that goes beyond quantum computing and touches on some fundamental ideas about creativity and innovation.
It definitely gives us something to ponder. But aside from these philosophical questions, are there any practical concerns about AI designing quantum algorithms?
One of the main things we need to watch out for is bias in the AI models. If we're not careful about how we train them, we could end up with algorithms that are biased or that don't fully grasp the complexities of quantum mechanics.
So it's like teaching someone to cook. You don't give them clear instructions and proper supervision, you could end up with a real mess in the kitchen.
That's a great analogy. We need to make sure these AI models are learning from the best possible sources and that we're training them to explore all the options, not just the easiest or most obvious ones.
It's been an incredible journey exploring this fascinating world where AI and quantum computing intersect. We've seen how AI can help us design and build these incredible quantum computers, create more efficient algorithms, tackle the challenge of errors, and even help us understand the results.
And we've only just glimpsed the possibilities of a future where AI powered quantum computers might be able to solve problems that are completely beyond our reach today.
It's a future filled with promise, but it's also a future that demands careful thought and responsible development. We need to make sure that AI is used to enhance our capabilities, not to replace or diminish them.
Well said. As we reach the end of our deep dive into this incredible frontier, we'll leave you with one final thought to consider. If AI can unlock entirely new capabilities in quantum computing, what are the ethical implications of this power? And how can we ensure it's used to benefit all of humanity?
That's a question that will become more and more important as we continue to explore this uncharted territory. Thanks for joining us on this deep dive.